This part of the lecture will focus on design considerations of distillation column. You will need to recall material learned and in distillation and absorption unit and multi-component engineering separations as well. So here we will not talk about the detailed step-by-step design of a distillation column, but we will focus on different design parameters which affect the performance of a distillation column and its economics. So distillation is a very important separation technology in process industry, and when we decide, for example, a separation unit in our process, we normally look at the economics of the separation unit, the volume to process as a feed, and then the throughput of your separation unit, and then finally we look at the recovery and purity of your system, the purity of the product. And another important factor that we look at is the reliability of technology and distillation, because it's one of the very old technologies. So there has been a lot of investigation into design of distillation columns. So this technology is much more reliable compared to new technologies like membrane technology. So distillation is very commonly used if you have a liquid feed that has a tendency to vaporize as well. Normally, heat is used to vaporize the liquid, and it is very effective if you have a component composition of 10 to 95% of your stream. Okay. Distillation is very simple to upgrade as well. It requires low capital cost, and you can actually scale up very easily. So compared to, for example, membrane technology, it is much more effective because membrane technology, it is very difficult to stage up or scale up. So as we discussed in part one, that in distillation, separation is achieved by exploiting the difference in volatility of components being separated. And also in distillation, we take advantage of very large density differences between the liquid and the vapor phase to be separated by using the gravity effect. And in distillation, normally we have an upward vapor phase where we use heat to generate that vapor phase. But at the same time, condensation is also an intrinsic part of distillation, because we need to condense the overhead vapor to get the countercurrent liquid flow in the system. Despite several advantages of distillation column, like in terms of its low capital cost, its reliability, scalability, there are also several situations where we might want to find an alternative to distillation. And this slide shows some point that we might want to consider when we are deciding if distillation is the separation technology of choice or not. Okay. So the first point here is that the low boiling components present a challenge. For example, condensing them to provide a reflux can be very costly, either because condensing needs to take place at a low temperature, or because the high pressure are needed for condensing. Secondly, large molecules are sometimes sensitive to high temperatures, such as their own boiling points. It means that if you heat them, they might degrade or decompose before actually they reach their boiling point. One way around this situation is that we do distillation under vacuum, but as you can imagine that vacuum brings additional challenges and costs in terms of the safety of the operation, but also the capital cost, because you need much thicker walls and special materials for vacuum. Third, we have that if a component is present only in low concentration in the feed, distillation might not be the best option, because distilling to produce relatively pure stream of that component may not be practical solution. Yeah. So you can imagine that if only a small flow rate is withdrawn as a product, that implies that there is very large flow rate of the material being circulated as reflux internally within the column. And this large flow implies that the equipment would be much larger, because it needs to handle that reflux. But also the heating and cooling of that circulating material could be very expensive, because the bigger the liquid flowing inside the column, the more vaporization you need to provide. So it means a bigger reboiler, and also you need to do condensing, so it means that you have a bigger condensing heat duty as well. Fourthly, we look at different classes of compounds that may need to be separated, but it may not be possible to separate materials into different classes based only on their volatility. And an example can be separation between aromatic hydrocarbons and aliphatic hydrocarbons. So what are these aromatic and aliphatic hydrocarbons? So aromatic hydrocarbons are the molecules where you have aromatic rings like benzene structure, okay? And aliphatic hydrocarbons are linear chain carbon branch, for example, molecules where you don't have these aromatic rings. So just based on their volatility difference, it would not be possible to classify them because they have same molecular weight, so it means that they will have very similar properties in terms of their separation. The fifth point that you might want to consider is that if your mixture has low relative volatility or azeotropic behavior, and what it means that if the equilibrium composition of the liquid and vapor phases are similar, then little separation can take place on each distillation stage. And this implies the need for large mass or energy flows, or could simply imply that the separation cannot take place because of the azeotrope is being formed and the azeotrope cannot be separated into its constituent components. And the final point is that if the mixture contains low boiling points that we normally call light components and much heavier boiling components, like the case of condensable components and non-condensable gases like nitrogen, oxygen, then we may just want to use a flash drum instead of using a distillation column. So why we should use flash drum if we can for separation? Because flash drums are much cheaper in terms of their capital cost, and they are much less complex in design compared to a distillation separation system. So if you have a mixture of condensable and non-condensable components, or very light components and very heavy components, then flash drum is always preferred compared to a distillation column. So this slide focuses on when distillation is not suitable, but notes that the distillation is still used in these cases, even though it is not suitable. Okay, so these points are just some general considerations, but depending on your whole process, distillation might still be the best separation technology compared to other units. Once we have decided to use distillation as our separation technology, we also need to choose the operating conditions. And the most important operating condition is the pressure. Okay, it is also the most complicated condition to choose. If you increase the pressure of a distillation column, keeping the feed and the product compositions the same, there are several things that can happen. Firstly, the separation becomes harder. This is evident from the decrease in relative volatility. And as a result of lower volatility difference, the minimum reflux ratio and the number of stages also increase. And because obviously by reducing the relative volatility between components, the separation becomes harder, and now you need a taller column or much heavier reflux flow to separate them. The increase in operating pressure also increases the boiling point of your components as well, and that in effect actually increase the temperature of the distillate and the bottom product as well. And this increase in temperature of the product and the distillate can also increase the temperature and the duty of the condenser and the reboiler as well. An important point to note that the heat of vaporization actually decreases with increasing pressure. So per mole of the vapor produced or condensed, the heat duty will decrease. However, because the molar flow rate of the vapor increases as the reflux ratio increases, the duty of the condenser and the reboiler may increase or decrease as the pressure increases.